So if you did go to YouTube and you looked up Mr. Stapleton and you found my YouTube channel, you would see this being streamed right now, but there would be a little bit of a lag. So flipping through this, let me just go through here. The first few pages are about mass, volume, density, and weight. So we've talked a little bit about density, but this first sheet, second sheet, third sheet, that's kind of all this stuff. Mass, volume, density, and weight. Just really knowing well what those things are and how they relate to one another. The next part is how temperature relates to motions of molecules and pressure. So when we get to here, you can see temperature affecting volume and pressure. And then the last part is how squeezing and releasing a gas can cause the temperature to change. So those things are going to help us understand what's going on in stars. So these are all necessary for understanding astronomy. All right, first thing I want you to do is I want you to try to guess what goes in these blanks. So there are 4 definitions here. I'll be talking about my favorite definitions, but one of these things means the amount of stuff in something. The next one is the amount of space something takes up or how big something is, size in 3 dimensions. The next one is how compressed or crowded the stuff inside an object is. And the last one is the force of gravity pulling on an object toward a planet. So those are the 4 words. See if you can put the 4 words in the right blanks, and then we'll move on from there. And your homework is going to be to do the 3rd page of this. I'll give you a little time. I'm going to come by and see how you're doing too. One of them has the answer right there in the definition. Whatever you do, it's not my choice. Hey! Oh, so that's, yeah, it's exciting if they're on the screen. All right, so my hand has appeared here, but not on your computer. It'll appear there in, I don't know, maybe half a minute. Don't turn the volume on or it'll get really weird in here. So the one that gives everything away, and the answer is this one. Density is mass over volume. So this is probably the one I'll be harping on the most. And the definition I like to use is crowdedness. So that's density. Something's really dense if all the stuff in it is packed in really tight. Stuff, the reason I use the word stuff is because I think it's helpful. The answer here is mass. But if we look up a definition of mass, sometimes you'll see a definition that will say it's the amount of matter in an object. Like anything that, yeah. And then if you look up what matter is, it'll say anything that has mass. So it's not really helpful, but it's stuff. So things that don't have mass are very few, but it's things like feelings, love, sorrow. Those don't really have mass. They're not really stuff. Anything else, this paper, the air around us, anything that's stuff has its mass. The amount of space something takes up. So we've got 2 choices. Is that volume or weight? Volume. And in general, I kind of like it when we just talk and blurt out. If you want to raise your hand, you can do that. And I'll try to remember to call on people, but a lot of times, if it looks like it's okay to blurt out, it's okay. And if I ever need you to raise your hands, I'll tell you to raise your hands. But just letting you know, I'm kind of loose on that. So the force of gravity pulling an object toward a planet, that is weight. Okay, so those are the 4 definitions. These are questions and these are pictures that test your application of those 4 definitions. So the way this works is this line right here, this circle, this is the edge of object C. It's infinitely thin. So this edge right here is just to show us where, like, this is part of C and this isn't. But there's no stuff there. It doesn't count in terms of stuff or mass. That's just the edge of it. The only mass inside object C is these 2 dots. You can think of these as being BBs, little, or marbles or whatever. All these things have different numbers of BBs or marbles in them. That's the stuff. So there's stuff here, there's stuff here, there's nothing here. Does anybody know the term, the scientific term for nothingness? A place where there's nothing. It's called a what? A black hole is sort of a place where there's lots of stuff. We'll get to that later. A black hole is where, if you had a black hole right here, I'll just make a little mark. It would suck in all this stuff over here, and it would all get squished into that little point. And then around the black hole, the black part, where we can't see, there really wouldn't be anything there, but that's just where light can't escape. But the word I'm looking for is a vacuum. So a vacuum means nothingness. So this is all a vacuum, nothingness. All the stuff is right there. So you can see some are bigger, some are littler, some have more stuff, some have less stuff. So see if you can answer these questions now. 5, 6, 7, and all the way through 12. Which one has the greatest volume, which just means the one takes up the most space, the biggest one, the one with the most size. Which one has the least volume, so on and so forth. So try those. It's not supposed to be really hard. It's supposed to be pretty simple. But you still might miss some, and that's okay. Let's see. Some of you are getting most of these. But some of you are. Some of you don't seem to even know what I'm asking. So let's go over the answers. Which object has the greatest volume? Which one's that? It's E, Y, E. It's the biggest. Doesn't matter how much stuff is in it. Volume is just size. So I tried to make the thing that I feel like is the most concise definition is the bold word there. So the least volume would be the smallest one. And which one's smallest? A. So B has the least amount of stuff in it, but you can tell A is a little bit smaller than B. You should be able to make that out. So A is the smallest. A is the least volume. All right, greatest mass. So which one has the most stuff in it? F. And to figure out how much stuff is in there, you just have to count the BBs or count the dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This one has 12 units of mass. This one looks like it's next. It's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So not quite as much stuff, so not quite as much mass. So the most mass is F, but it's not the biggest. Which one has the least mass? B, but it's not the smallest. Density, which one is the most dense? Which one's the most crowded inside? D. If you look at how much, if you think of these dots as people living in a house, each of these dots has the smallest amount of space. If we divided this house into a separate room for each dot, they'd be tiny little rooms. So D is the most crowded, most dense. Which one is the least dense? C. And if you're thinking, well, maybe it's B, just do this. Just divide this up into equal size rooms. This dot gets a room this big. This dot gets a room that big. This one only gets a room that big. So it's definitely the least dense, least crowded one is C. One thing that I haven't put on here, and maybe we'll get to that in a little while, which one of these terms so far, volume, mass, or density, which one determines whether something sinks or floats? Oh, did I steal your balances?
Yeah.
Take them back. I saw them in there. I thought, these are probably Mr. Walgorski's.
Cool. Thank you.
They're nice little balances. Sorry about that. Okay, we'll have to just use this. We'll share this balance today. So, anyway, so what was the answer? What determines whether something sinks or floats? Is it how big it is, how much stuff is in it, or how crowded the stuff is inside? How crowded the stuff is. Density. Density determines whether things sink or float. That's a super important thing to remember, and we'll use that a lot. Now, I've got some asterisks here, and we'll talk about 13 in just a second, but which one weighs the most? Which one would be heaviest? So force of gravity pulling on an object just means, got this mouse here. In order to pick the mouse up, I have to fight against gravity. Gravity's trying to pull it down. So I have to exert a force that's stronger than the weight of this in order to lift it. That's what weight is. And weight tells you how heavy things are. So which one do you think is the heaviest? We haven't really been over this. If you had to pick up one of these things, or all of them, this one is empty except for 2 BBs. This one's empty except it has 1, 2, 3, 4, 5, 6, 7, 8 BBs in it. This one's empty except for 1 BB. This is empty except for 12. This is empty except for 10. Which one's going to be heaviest? What letter? It's F. So weight and one of these other terms, they go together. And it's mass. Weight and mass go together. The more stuff you have in you, the heavier you are. So an example that I've talked about before is D is really dense because it's really crowded inside. That'd be like a rock. If I threw that in water, what would happen? It would sink. F is not as dense, but it's still pretty heavy. This might be like a little boat, or let's say a ski boat. I throw a ski boat in water, it floats. So because it's not as dense as this, but it's got more stuff in it, so it's heavier. So I'm getting kind of distracted. But whatever we choose for these two, we're going to have the same answers down here. The more mass you have, the more you're going to weigh. Except. So let's say, I'm just making this up. I'm going to draw a couple of people. Here's somebody who has 100 kilograms of mass. And here's somebody who has 50 kilograms of mass. If those people were in here right now and you tried to pick them up, this person would be a lot harder to pick up than that person, twice as hard. But it's possible for them to have the same weight. How can two things that have different masses actually have different weights? Parker? So if these were bigger BBs and these were smaller BBs, well, that would still affect the mass. So if you had all these BBs that were twice the volume of these, then each one of those would count twice as much for mass. So it's something different. It has to do with the definition of weight. Weight is the force of gravity pulling something toward a planet. Prosper? How can these people weigh the same? Right. So where could I take them and neither one of them would have any weight at all?
Space.
Outer space. If you took these people far from the Earth, their weights would both be what? 0. So they'd have the same weight, right? So all these things, in these kinds of questions, the one with the most stuff in it is going to weigh more than the one with less stuff in it. This is going to be the heaviest. This is the lightest. But I just want you to know that if you go to a place where there's no gravity at all, this one still has stuff. It just doesn't have weight anymore because the force of gravity is gone. So the asterisks, there are asterisks above because in special circumstances, all the objects can have the same weight. Explain. So if there's no gravity, all objects zero weight. So we've got these 4 definitions, and this is one way to practice using the definitions. This is really kind of a straightforward way. And then we're going to do a little bit of some examples. And your homework is to do some more examples. I'll wait a little bit while people finish up here. What time do we get out of this class? We need to learn this. I don't even remember. Yeah, so the next class starts at 1:55, so we get out of here at 1. Oh, no. We have flex next. 1:20, so we are done at 1:15. All right. I'm going to write that on the board. 1:15. Make sure that before then we clean up and do whatever we need to do to get ready to go. It's 12:33. Still got a good amount of time. All right. Flip to the back. This is what your homework's going to be like. So we're going to do 14 through I just noticed there's no 18. Doesn't matter. We're going to do 14 through 19 together, and your homework is to do 20 through 24. Does it have to be right in order for you to get full credit? No. This is just practice. Just about everything we do, everything except the test is practice or a game or something. All right. So I'm going to make a ball of aluminum foil. My mom moved from Georgia, the state of Georgia, to Vermont to live near us, and she had so much aluminum foil. We have this everlasting supply of aluminum foil. So I've made my aluminum foil into a ball right here. All right, ball of aluminum foil. And the way this works is I'm going to do something. I'm going to do this. I'm going to squeeze the aluminum foil into a smaller ball of aluminum foil. And then for each of these, we're going to have to tell, did this increase? Did it decrease? Did it stay the same? And then write some brief explanation there. Prince, will you stop making those noises? Okay, so here we go. Going from this to that. All right, what happened to the mass? Actually, yeah, so think about it. Raise your hand on this one. Raise your hand if you want to answer. What do you think, Ian? Nothing happened to the mass. The mass stayed the same. And Ian, how do you know? How do you know the mass stayed the same?
You didn't add anything.
I didn't add any stuff, and I didn't take away any stuff. So you could say this however you want to. I'm just going to say no stuff added or removed, because there's not much space to really say much. That's how you change mass. You either have to take something away or add something. All right. Raise your hand if you can tell me what happened to the volume. Prosper. Volume decreased. I'm going to use minus. So Prosper, how do you know? Like what makes you think the volume decreased? Yeah. Ooh, that made me think of something else. Well, I'll come back to it in just a second. But mostly for the explanation, I just want you to know, I want to know that you know what volume is and how to apply it to this situation. So it got smaller. I'm just going to say it got smaller. But Prosper said something interesting. He said, I removed the air from it. Is that true? Was there air inside it before?
Yes.
Is it gone now? Is there stuff in air? Yeah. So technically, we could actually say the mass decreased a tiny bit. I'm not going to. The mass stayed about the same. If I had put this on the balance, the electronic balance and we measured, and then I did it, so it wouldn't, removing the air didn't change it much. But if you wanted to tell me that on a test, if you wanted to say the mass decreased a little bit because you got rid of the air and air has stuff in it, that's fine. Okay, density. So raise your hand if you can tell me what happened to the density. And there's one word that I think could make this easy if I reminded you. Naya? Increased, yeah. So why do you think it increased? How do you know? How do we know? Well, density isn't just how heavy something is. You can have something, again, like an aircraft carrier that floats, but it's really heavy. But the fact that it floats means it's less dense than water. So what's the key word with density? What's the bold word on the other side? Anybody? If you look back at my definitions, it's the crowdedness of it. So if you lived inside this foil ball, would you be more crowded or less crowded than before? You'd be more crowded. So density is all about how crowded things are. If you compress them, you make them more crowded and you make them more dense. You can use math to calculate it too, but we're not going to get into the math too much. I'm going to say it got more crowded. And I'll say more crowded inside. Another way to do this is to think about this. By compressing it, do you think that this would now sink or float? It might sink, it might float, but if I kept squeezing it, making it smaller and smaller and smaller, would it eventually sink? Yeah, so I'm making it more likely to sink than before. Before it would definitely float. Now it's probably getting closer to sinking. If I took a hammer or a vise and I kept squeezing it, I could probably get it to sink because aluminum sinks. And finally, weight. Did this thing, I wish I'd had the balance, but if I weighed it before and I weighed it after, do you think we'd see a difference in the weight? I can do that. I think the cord is long enough. Move this over, zero this thing. I could go the opposite direction and I could try to fluff it up, but it's too much trouble at this point. Okay, so 0. Ooh. This balance isn't really seeming to work. Okay, so I don't know that we'll be weighing things today, but it says 19.9. To put this on, now it says 24.85, 86. It's varying a little bit. It's between 24.84 and 24.86. It actually does look like it got a little heavier according to this balance. But this balance is bad. It should, the weight really shouldn't change. Because it's complicated. Have you ever heard of buoyancy? So buoyancy is a really tricky thing. But I'm just going to tell you that when I squeezed this, if anything, it lost a little bit of air. And air does actually have mass, and it does have weight. So if anything, theoretically, if I had a good balance, if the weight was going to do anything, it should have gone down. But it really should have stayed about the same. Sorry about this bad balance. I'll see if I can borrow some of the ones Mr. Giampa has. So the easy way to do this is you can write the same thing for weight that you can write for which of these other ones. Which one determines something's weight? Its size, its crowdedness, or the stuff inside it? I want to make something heavier. What's the best way to do it? Change the size, change like how compressed it is, or add stuff to it? Add stuff. So whatever happens to mass generally happens to weight too. So if that's equal, this is equal, and I'm just going to write for my explanation, same as mass. And I can write that every time, except you'll see. In a little while, I'm not going to write it. Okay, now I have a piece of paper. It's actually just some paper towel. And it says, a piece of paper loses its corner when the corner is cut off and thrown away. So here's my paper before. Getting rid of this corner. All right, it's gone. Now there's my paper. All right. What happened to mass, which is the amount of stuff in the object? Did it change? Is there more mass or less mass? Less mass. So I remove stuff. How about the volume? How about the size of this? Does it take up more space or less space or the same space? I'd say less. Yeah, I mean, I'll do it again. Look at how much space it takes up. No, it doesn't take up as much space. So the volume decreased. Got smaller. Now, density. You lived inside, if you were just living inside here, right there, there's your house, living inside the paper towel, and I did this. Did I just make your house any more crowded or less crowded? Did I compress the thing? Did I fluff it up? Did I? So here, let me draw you in your house. There's me. I won't put you in this house. There. Somebody's living in that house inside the paper towel. I remove a piece of the paper towel from over there. Is that person more crowded or less crowded? Well, the same. Yeah, so here I guess maybe this is what I'm getting at. Let's based on your answers, I need to draw a new picture. This isn't the kind of paper I was hoping for. So how about this? Let's see if I can organize this. I'm going to try to evenly space some dots out like this. I didn't do a good job of evenly spacing them. Okay, so I rip this right here, and I get rid of this part. Do any of these dots feel more crowded than before? So the amount of space that each of them has, if I divided this up into rooms, I could divide it up into rooms like this. This is the room, this is the room, this is the room. If I get rid of this piece, their rooms don't get any smaller. If I get rid of this piece, their rooms don't get any smaller. So unless you see me like take this piece right here and squish it down to a tiny size, that makes them more crowded. But just removing this right here doesn't affect the size of this room. So that's kind of a tricky one. Unless I'm squeezing it or fluffing it up, which we'll get to in a second, the crowdedness should be about the same. So I'm going to say density didn't change. Now, another way to look at this maybe is, do you think if I threw this on some water, it would sink or float? It would float for a little bit. What if I threw this on water? Would it float for a little bit? So by removing this, I haven't really made this more or less likely to float. It'd be like, another example would be if I had a piece of wood, a block of wood, and I cut it into two pieces, would the two pieces still float as well as the single block? They'd float, they just float separately. So when you remove part, you don't really make the rest of it more compressed or less. So density, I'm going to say the remainder was not compressed or spread out. You could also just say I didn't change the crowdedness. So here's my paper. I get rid of a corner. Heavier or lighter now? Lighter. It decreased. And it decreased because I got rid of stuff. So mass decreased. And whatever mass does, weight does the same. I wish I had a bike pump, but I don't. Because if I had a bike pump, you wouldn't have one complaint here. So you see, I'm going to try this really bad scale, which now says 20 and can't be zeroed. I'm going to write this down, 21.7 or 21.77. Now I'm going to blow up the balloon. Tie it off. Oop. Yeah, just do this. So there's the balloon now. And you know how balloons are. They seem so light, but if I put this balloon on the scale and measure the mass, or measure the mass, it's going to be hard. First of all, I should have put a thing on here to help me balance it. Ah. The wind is blowing it off of here. I don't know if you can you see the 20, it's almost 22. I don't know if you can see that down there, but it did. It goes, wah! Is anybody freaked out by popping balloons? There's some people who really, really don't like popping balloons. I should have warned you that I like to pop balloons, although I didn't pop that one on purpose. Okay, so here we can make a decision. We can make a decision about how picky to be. So when I blew up the balloon, I inflated it. Did I change the amount of mass it had? Did I add stuff to it, or did I take stuff away? I added what? Air and my breath. And what's in breath? CO2 and also water vapor. And that's why, has anybody ever been in a tent or a small space and when you're sleeping and you wake up and there's dripping all over the place? That's all the air you breathed out, and the water in your vapor in your breath is condensed. So when you blow up a balloon, whether you use a bike pump or whether you use your mouth, you only add a little bit. So I guess I'm going to include it. I'm going to say yes. So I added air, which has a little mass, which is stuff. So I added some air. How about the volume? Did the volume of the balloon increase or decrease? Increased. And how do we know the volume increased? It got bigger. Now, what would be a good test to see if it got more dense or less? First of all, do you think it got more dense or less dense as I blew it up? Less dense. And what's one way you could explain how you know that? That's not us. We've got 25 minutes. How do we know it became less dense? And what's a test we could use? If I had that balloon, if this was the balloon and I had it right here, I could do something with it and then blow it up and do the same thing with it, and I could see the difference. What would I do, Prosper? That we're going to do sometime. So that one's kind of a tricky one. But let's say I tossed it in a pond, would it float better when it's inflated, or would it float better before I blow it up? It would float better when I blow it up. So if it floats better, that means it's getting less dense. Also, think about that balloon. It looked like this in the beginning, and it looked like this at the end. Is it getting more crowded or more spread out? I'm going to go with that one. I'm going to say the density decreased because it spread out, so it was less crowded. Now I filled it with air, and you could say, oh, it's crowded with air, but is there a lot of stuff in air? Air is mostly empty space. I mean, most things are actually mostly empty space. Weight, I tried to show this. It was a very bad demonstration, but if the mass went up, guess what happened to the weight? It went up too. I'm just going to write same as mass. And I'll try to give you a better demonstration of that in the future. This next one's the last one we're going to do together. I don't have a moon rock or a rock. Yeah, I don't have a moon rock, but let's say this is the rock on the moon. I go to the moon, I pick it up, I bring it back to Earth, I set it down. This is what it looks like on the moon. This is what it looks like on Earth. Of all these things, what's going to change? The weight. What's going to happen to the weight when you take it from the moon to the Earth? It gets heavier. So the weight's going to increase. And why does it increase? Why does it weigh more on the Earth? So there's gravity on the moon too. Where's gravity stronger? So Earth's gravity is stronger. I'm not going to write stronger than the moon's gravity because I don't have space. But if this is what it looks like on the moon, and this is what it looks like on the Earth, have I changed its mass? Have I added stuff? Taken away stuff? Is there any change in mass? No. So no change. Stuff. Okay, how about volume? What would we see if the volume were changing? Would get bigger or smaller, right? Would this rock be any bigger or smaller? Nope. Same size. And now this one, if you've got the same amount of, so I usually use mass as furniture. Think of mass as the furniture in a house. And think of volume as the size of the house. If we've got the same amount of furniture as before, and we have the same size house, is there any way it can be more crowded? Or less crowded? No, it's going to be the same density. So same stuff in the same space. So I'm just going to write equally crowded. And the homework was to do just I think we should stop there because I know you're tired of listening to me. But the homework was to do this page. I think I'll just keep it as that, and maybe we'll do number 19 together tomorrow. So do the same thing we did for 20 through, how about this? You can do it through all of it, for all these except for one. Hi. So what do you go by? Are you Tio? Or, okay. All right. Tio, let me tell you where your seat is. Got a seating chart. I'm going to stop.